Hello guys and welcome to my video. So today we're going to be focusing on the November 2014 question paper 2.2 for physics, and the question paper is 1 hour long actually. So we're going to try to move as fast as we possibly can so that we can be able to answer as many questions so that everything hopefully makes sense. So we're gonna move a little bit fast. Okay, starting off with the first question. The Young modulus of a metal wire is 1.8 times 10 to the power of 11. The wire is extended and the strain produced is 8.2 times 10 to the power of -4. So we want to calculate the stress in gigapascals. What do we know? Always start with what you know. We know that the Young modulus, okay, we know that the Young modulus is equivalent to the stress divided by the strain, right? So in order for you to find the stress, you have to multiply the Young modulus and the strain, right? Because Young modulus basically measures if you have a metal of a specific wire, it's going to have a specific Young modulus, right? It sort of measures how much stress can you apply to that metal and how much strain can it experience, strain being the extension per unit length. So it probably means that your stress will just be equal to your Young modulus times your strain, and that is just going to be equal to your Young modulus is 1.8 times 10 to the power of 11 multiplied by your strain, which is 8.2 times 10 to the power of -4, right? And then that's going to give you an answer of 1.4761234.5, right, pascals. But the question asks you gigapascals. As you can see on the screen, we have multiple prefixes that you're supposed to know, and on that screen, let's just take a piece of the pie. For the gigapascal, you can see that 1 giga is basically 10 to the power of 9. So if you want to express this in gigapascals, it's basically 1.4761234.5 divided by 10 to the power of 9. So that's just going to give you 0.148 gigapascals, right? So we have 0.148 gigapascals. Moving on to B. An electromagnetic wave has frequency 12 times 10, 12 terahertz. Calculate the wavelength in micrometers. Okay, so electromagnetic waves, they basically come from the sun. So you see the sun shining on us, lovely. You see the light that you see, that's the visible light. So it's part of the electromagnetic spectrum, things that come from the sun. There are probably other waves that come from the sun as well, but we've just been told that there's frequency of 12 hertz, and you want to calculate the wavelength. What do we know? Always start with what you know. You know that V is equal to F lambda, right? So the V will be equal to F lambda. So if you want to find the wavelength, which is lambda, it will just be equal to V over F. But when these waves come from the sun, they're very much running, right? It's 3 times 10 to the power of 8 meters per second, right? So they cover almost millions of meters in 1 second. So in order to get lambda, 3 times 10 to the power of 8 divided by F, your frequency, which is 12. Tera is basically times 10 to the power of 12. Then that's going to give you 2.5 times 10 to the power of -5 meters, right? So if we divide this by micro is essentially, right, if you look at this, micro is essentially times 10 to the power of -6. So it means here we're going to just divide by 10 to the power of -6. That's just going to give you 25. So your correct answer will be 25. So the name of the region of the electromagnetic spectrum for this frequency, as you can see, this frequency is essentially part of the infrared. As you can see on the screen, infrared basically ranges from 10 to the power of -2 to 10 to the power of -6. So definitely 25 times 10 to the power of -6 has to lie in that. Remember, I said that micro refers to 10 to the power of -6. So we're going to have 25 times 10 to the power of -6 being a part of that. So our answer is just going to be infrared. Okay, let's write it in red, right? Infrared. Move on to C. An object B is on a horizontal surface. Two forces act on B in the horizontal plane. A vector diagram for these forces is shown to scale. So we're given an object B. So B, this is essentially our object, right? And then two forces are acting on this. So it's being pushed in this direction and pushed in this direction, right? And then vector diagrams have been shown for those specific forces. A force of 7.5 towards north and a force of 2.5 from 30 degrees north of east, right? So if you're here, if this is east, right, north of east is probably going to go like that, right? North of east. On figure 1.1, draw an arrow to show the approximate direction of the resultant of these two forces. Okay, so if you're looking at this diagram, right, just think about it. If you're pushing something up, it's supposed to move up, right? But if you're pushing something on the side, it's going to be tilted, right? It's essentially just going to move in this direction, right? Because you're pushing it up, okay? And then when you're pushing it up, you're now pushing it on this specific side, right? So if this is your y-axis, right? If you're going to continue this is north, right? If you're going to continue it like that, this is not our diagram, guys. We're just making an illustration. If this is north, right, and you want to draw your resulting force, you can see that this 7.5, guys, is one of the biggest things that you have, right? 7.5 newtons acting up on this specific force. But if you're gonna move, apply force like this, it's gonna tilt. It was supposed to just go in this specific direction, but now it's gonna tilt because you're applying 2.5 tilted from that side. Okay, so it essentially means that the overall force that you're now gonna have will be towards this direction. Okay, like so. Right, something like this, right? So essentially, we were supposed to have, a resulting force of 7.5 just acting up on the object, but we pushed it like this, so it's supposed to go like this. So what is Cambridge looking for? They're looking for an arrow, right? They're looking for an arrow that is drawn to the left of the 7.5 Newton force. So if the arrow is on this left, you're cool. Right? And then if it's 5 to 4 degrees, right, 5 degrees to 40 degrees, sorry, west of north, okay, 5 to 40 degrees west of north, then you get your other mark, west of north. What does that even mean? It means that this is north, so this is west of north. So that's supposed to be 5 to 40 degrees. So it's supposed to be almost closer to the north as possible. Why? It was just supposed to move to the north, guys, but now it has been tilted a little bit by that 2.5 Newton force. Does that make sense? I hope it makes sense, right? Moving on to the next question. Show that the magnitude of the resulting force on B is 6.6 newtons. Okay, if we look on this diagram, right, we have a force going up of 7.5 newtons, right? Force going up, 7.5. Look at this 2.5, right? So this 2.5 has two directions. If you're going to be fancy, resolve it in two directions, you're going to get a force like this. Okay, a force that's acting down at this specific point, right? Why? Because, well, that 2.5 is acting that direction, right? And then if you're going to resolve it in the other direction, right, you're going to get a force that's basically looking like this, okay, in this direction, right, like so. Okay, so you have two forces, right, acting in two specific directions, one in that direction and one in that specific direction. So what's going to happen if there's 30 degrees here, you can sort of see we have a z, so this is going to be 30 degrees as well. So if you have 2.5, this is the opposite of this 2.5, so this is going to be 2.5 sine 30, right? So we have 2.5 sine of 30. Then this is going to be 2.5 cos of 30. These are the two forces acting on our body. We have a force going in this direction, then a force going down like this, right? So you can sort of see to get this resultant, these forces are sort of opposing each other. So we can sort of check in the horizontal. Okay, in the horizontal, we only have one force, right? We only have one force acting in this specific direction, and that force is just 2.5 times cos of 30. That's in the horizontal, right? But the flip side of that, number 2, in the vertical, okay, in the flip side of that, in the vertical, we have probably a force going down like so of 2.5 times 10 times sine of 30. So it's 2.5 times sine of 30. Then you have a bigger force that's acting up, which is just 7.5. So it means that these two are fighting. So overall, we're going to have a force of 7.5 minus 2.5 sine of 30. It's going to be our overall vertical force, right? 7.5 minus 2.5 sine of 30. What does this mean now about our resultant? Our resultant now consists of two things, one in the horizontal and one in the vertical. So if we were to draw a little triangle, let's be a little fancy. If we have a scenario like this, okay, if you look at this carefully, like I've said, here we have 7.5 minus 2.5, okay, sine of 30. Then on this side, we have 2.5 cos of 30. And then you want to find this. This is the hypotenuse, guys. So you can sort of say this is A, this is B, and then this will be C. So if we want to find C, we have to go back and use something that, sort of steal something that, say, Pythagoras came up with us. Thank you very much, say, Pythagoras, right? He came up with this theory called the Pythagoras theorem, right? So we'll sort of help us find C. So what does it say? It says that C squared will be equal to A squared plus B squared, right? So essentially, 7.5 minus 2.5 sine 30, that's basically 6.25. 2.5 cos 30, punch that on your calculator, you get about 5 root 3 divided by 4. So it means that your value of C would just be the square root of 6.25 squared plus 5 root of 3 over 4, all of that squared. So your value of C is just going to be about 6.614 and so forth, so forth, so forth. So it's basically just going to be 6.6 newtons, rounded off. Approx. Calculate the magnitude of the acceleration of B produced by this resultant force. What do we know? We know that the resultant force is equal to your mass times your acceleration. So if you want your acceleration, it's going to be your resultant force divided by your mass, right? But in this case, your resultant force, guys, it's 6.6, right? 1, 4, so forth, so forth. What is your mass? What is the mass of this B? Right, about okay, we're given the mass here. Okay, we're given 750 grams, right? So like I don't know, an apple or something like that. What weighs 750 grams? Okay, so we have 750 grams. So it's going to be 0.750. If you divide this, you're gonna get about 8.8 meters per second squared. So you're gonna have 8.8 meters per second squared, right? Now, I want to determine the angle between the direction of acceleration and the direction of the 7.5 Newton force. Direction of acceleration, what does this even mean? Direction of acceleration, well, this is also the direction of the resultant force. Because acceleration, resultant force, they are in the same direction. So you just want to find this direction from this direction. So this is the direction of the 7.5 Newton force because it's acting up. So we want to find basically this angle theta, right? That's the angle theta that we just want to find. How do you go about it? Well, if you think about it, this 2.5 is sort of your opposite. Then this 7.5 minus 2.5 sine theta is sort of your adjacent. So in order for you to find the direction, the angle, you can sort of rely on trig ratios. Okay, so basically tan theta is basically going to be equal to your opposite divided by your adjacent. Okay, so tan theta will be equal to your opposite, like I said, is basically 5√3 divided by 4, because it's this cos thing, right? Divided by your adjacent, which is 6.25. Okay, so essentially theta will just be arctan of 5√3 over 4 divided by 6.25. So the angle theta would be 19.1066. Physics is fun. Solve problems and you're done. You get 1 mark. Heavily undercompensated. They're not paying us enough marks, but we'll accept it. All right. Other methods, you could go for scale drawings. I wouldn't really encourage that. That's pretty difficult, but it's doable. It's doable. Question 2. A ball is thrown from A to B. So this is point A, and then this is point B. Okay, as shown in Fig 2.1. The ball is thrown with an initial velocity v at 60 degrees to the horizontal. So we have a goalkeeper, right? Goalkeeper is standing on their goalpost. What goalkeeper do you know? I don't really like soccer. I don't know much about it. Let's say De Gea, right? I know De Gea. I've seen him a couple of times. So De Gea is standing at point A, right? He's at his goalpost, about to throw the ball. Yay! So De Gea holds the ball, then he throws it up in the sky, right? So that it can reach point B, where we have a striker. We have a striker over there. What striker do we have? I don't know. We have a specific striker that is standing over there. Let's say Mbappe, for example. I don't even know if they're on the same team or something, right? So we have De Gea over there, takes a ball, throws it off, then it reaches Mbappe. If the ball is thrown, we want to find, it's thrown at an angle of 60 degrees. So as he holds the ball, he throws it at an angle of 60 degrees to the horizontal, right? So the variation with time t of the vertical component VV of the velocity of the ball from t is equals to 0 to t is equals to 0.6, right? I don't know if he gets to play soccer, but as he's throwing his ball in the air, we're sort of comparing the vertical component of his velocity. This is, guys, your vertical component, and then this is your horizontal component. So we're sort of comparing that vertical component per unit time. Okay, so we've been asked to assume that air resistance acting on this ball is negligible. Complete Fig 2.2 for the time until the ball reaches B. We have B, right? So as it throws the ball, we want it to reach point B. So, it's going to start off with a very high velocity. It's going to reach 0. Why? Because it has arrived at its maximum point. And at its maximum point, velocity is actually 0 in the vertical. Because if you're at a maximum point, the only velocity that you have in this is in that direction, right? So your vertical velocity is actually going to be 0, right? And then it's going to reach B with the same velocity that it had to begin with. So if you look here, that's about 5.9. So if it took 0.6 to reach maximum height, it's going to take 1.2 to reach maximum height. So we're going to have a coordinate somewhere over here. So I'm going to take my little ruler and draw a line, right? So that you can be able to understand. So we're starting here, off here. Then we are going to there, right? Something like this. Okay, I hope that makes sense, right? So, go and try it out on your own. But essentially, it's going to continue from 0.6 up to 1.2. And then it's going to reach the same velocity, but now in the opposite direction. We have 2 marks. Cambridge. What does it want from us now, right? The first mark, they essentially want a straight line, right? So if you go here, they essentially just want a straight line. If you draw a straight line, you're done, right? You got some marks. Straight line from where? From 0.6 up until 1.2. Do not exceed 1.2. Okay, and then they want VV at that end to be negative 5.9. So this is number one. Number two, they want your VV to be negative 5.9 at 1.2, right? And you're supposed to have a line with negative values, right? Negative values as we're going down here. We're supposed to have negative values of VV. Okay, how is the maximum height reached by the ball? So as the ball is thrown by De Gea, we want to find out how much or how high can De Gea throw his ball, right? Let's see. So essentially, we can find it using Newton's laws of motion, very possible, or we can use a very simpler method. Just find the area underneath the graph, right? Because the area of a velocity time graph represents what, guys? It represents displacement. In this case, that displacement is in the vertical, and in the vertical, that displacement symbolizes what? It symbolizes the height. Okay, we have that, and we just want to find this area, right? We just want to find, basically, we want to find this area. What do we do, right? So essentially, what we do is we say half base times height. It's a triangle. What is your height? 5.9. Your base, 0.6. So if you go here, your max height, equal to your area underneath the graph, which is basically half a base times height, 1/2. What is your base? 0.6. What is your height? 5.9. Get you 1.77 meters. Come on, De Gea, I'm disappointed, right? 2 meters in the air. Come on. Now I was expecting like 20-30 meters or something like that, but no, who am I to judge, right? Now I want to find the horizontal component VH of the velocity of the ball at time t is equals to 0. If you look at our motion, guys, if you go here, we have an initial vertical like so of 5.9, okay, to begin with. So we essentially just want to find this vertical, this horizontal over here. So you can sort of see through these 60 degrees, 5.9 is the opposite, and then x, which is the horizontal that we want to find, is the adjacent. So you can apply a trig rule. So essentially, we can say tan theta is equal to the opposite divided by the adjacent. So tan 60, your opposite being 5.9, your adjacent being x. So x will be equal to 5.9 divided by tan 60. So 5.9 divided by tan 60, that's going to be about 3.4, 0.6366, somewhere thereabout. So it's basically going to be 3.4 meters per second. Okay. On fig 2.2, sketch the variation with time of VH. So we know that VH does not change. It remains constant. So we just want to sketch a straight line at 3.4. So if we go here, this is 2.2, 2.4, 2.6, 2.8, 3, 3.2, 3.4, like so. So you just want to sketch a vertical line, and you're asking, why does it remain constant? Because there is no acceleration in the vertical. So since there is no acceleration there's no acceleration in the horizontal. Because there's no acceleration in the horizontal, it means that the horizontal component of velocity is going to remain constant, and hence it's just going to be a straight line, like so. Makes sense? But it doesn't extend up into infinity like I did here. But it's going to end at 1.2, like so. Okay, so draw a horizontal line. That horizontal line should end at 1.2. And the graph said label. Guys, just follow instructions, right? We don't know what Kempe is going to do to you if you don't follow them, but you lose nothing. Just label it and then say VH. You're done. Okay. The ball has mass 0.65 kgs. Calculate for the ball the maximum kinetic energy. So we know that maximum kinetic energy is essentially 1/2 m times v squared. That's how we find kinetic energy, right? But we know that Vmax, right? We can find Vmax. So the velocity is going to start here. So he's going to throw it with a very high velocity, and that velocity is going to decrease until it becomes equal to the horizontal component, and it's going to increase in the opposite direction until it becomes maximum again at B. So the velocity, guys, is this V, not the vertical, not the horizontal, the combined effect of that V. So what it means is that we can apply Pythagoras, right? Pythagoras is back. Man, this guy has made history, right? So Vmax will just be equal to the square root of whatever you have in the horizontal plus whatever you have in the vertical. Okay, so your Vmax would just be equivalent to about 6.81 meters. So it means that it's being thrown all at the beginning with 6.81 meters. So it means that for me to get my kinetic energy, it's just 1/2 times my mass, 0.65 times 6.81. That's just going to give you an overall answer of 15 joules. Right, 15 joules. Okay, calculate the maximum potential energy above the ground. GPE, right? GPE is basically mg delta H. So if you want to find delta H, what is the maximum height that's going to reach? That's where it has the maximum potential energy, right? So your mass, 0.65 times 9.81 times your height, 1.77. That's just going to give you a GPE of about 11.3. So that's about just 11 joules, right? Why 2SF? Because look at this, 0.65 has 2SF, right? If you look here, you're going to ask me, where am I getting these marks from? Are they just coming out of nowhere? Not at all. For doing this, you get a mark. For working everything out, getting this velocity and all that stuff, because you have a valid method to find V, you're going to get another mark. You give them an answer, they give you a mark, right? And then if you're here, maximum potential energy, essentially give them a correct method with a correct equation, you get a mark. You give them a correct answer, you get another mark. Okay. Number 3, electric fields. We don't do that. If you're watching this from 2022 going on, unless it has been changed, but for now we don't do electric fields. So if you're preparing for an exam that is coming up, you won't need to look at electric fields for AS. So you'll be fine, right? As well as you know, molecular motion, Brownian motion, and materials, we don't also do that, right? Ductile and brittle, they're sort of out of the syllabus. So we're going to start off at number 5. A battery of EMF 12 volts. So batteries are labeled with what you call EMF. You're going to wonder, what is EMF, right? So if you look at a battery, you're going to see this little number written. For this one is 12, but for a normal battery, you might see 1.5. So it's normal small battery. So electrons carry charge, right? We've been told of convectional current and all that stuff, but basically electrons would carry charge from, let's say, over here. So when they arrive at a battery, they're given a bag of energy, right? Consider this bag of energy your EMF. So let's say it's given 12 joules of energy. That is what the energy is going to take, right? So EMF basically refers to the work done per unit charge in driving it across a complete circuit. The amount of energy that has been given to an electron so that it can move with it across a complete circuit. But because of chemicals within a battery, there's going to be internal resistance. So it means that this resistor, this little guy over here, is going to offer some internal resistance. This can be chemicals in a battery that's going to offer resistance to these electrons that are about to move. So it's going to lose some energy when it arrives here. So let's assume here it arrives with 10 joules. It has lost some energy when it has moved through R, right? So it has lost some energy. Now it is about 10 joules left. So it's going to use that, put it in X, get out, go back, get some more. So sort of like EMF. EMF, you get energy, a little bag, so your little electron is carrying a little bag with 12 joules of energy, moves around, drops some in the internal resistance, it's about 10, moves around, it goes to X, returns back to the cell. So that's basically a rough summarization, right? The current is 1.2 amps. Current is the rate of flow. How fast are these guys moving? That's just current, the amount of charge that passes through a specific point at a specific time. The same battery is now combined to the same two resistors, but now in parallel. So if they are in parallel, what happens is that electrons, when they arrive here, right? Electrons, when they arrive here, they have an important decision to make, right? I love the electrons. You know, electrons are clever. Be like an electron, right? So when they arrive here, we have a stream of electrons, right? Now we know that the electrons, back then they didn't know. They usually talk of convectional current, right? So if it's electrons, this is positive. Electrons would come from this direction, right? But convectional current would just be from this direction to that direction. Okay, but if we're talking of charge carriers, if you have electrons as they arrive at this point, right, they have a decision to make. They can either go up or go down. So all of them, they're going to go down, right? And some of them are going to go up. So they're going to split. They say, let's cover the same, same journey. You go up, we go down, right? They sort of split, little gang, right? But these guys still have 12. These guys still have 12 because they came from this same battery with the same amount of energy per unit charge. So it means that they're going to get into here with 12. So here we're going to have a potential drop of 12 volts. It's similar at that bottom X, you're going to have a potential difference of 12 volts. But if you look at this, they're going to share. They give 6 to this guy, they give 6 to that guy, right? And sorry, electrons are supposed to be on this side. But in conventional current, the normal current direction flow, always from positive to negative. Don't forget that. But that was before they found out that electrons actually existed. So we just stuck to conventional current. But in your brain, know that the charge carriers are electrons, the ones which take the energy and move them around. Okay, so in order for us to find the combined resistance, what we're going to do, we're going to get a little bit clever. We're going to go in series, right? In series, the combined resistance will be equal to X plus X, which will be equal to 2X, right? And then in parallel, the combined resistance is going to be 1 over X plus 1 over X to the power of -1, because it's 1 over R equals to 1 over X plus 1 over X, right? So this is going to give you X over 2, right? Evidently, we can see that, in series, right, the series connection is 4 times the parallel connection, right? We can see that. So we can write that ourselves, and then we can see, hence, right, in series, we have 4 times that in parallel, which is just 4 times X over 2, which is going to give you 2X, right? So we have shown that because we have 2X and X over 2, and we can see that if you multiply X over 2 by 4, we're going to get 2X. So Cambridge, when it's looking for, awarding you marks, you have found this and this, right? And then you're going to get an M1 mark for your method, right? But then when you have 4 times greater in series than in parallel, then you're going to get this mark. So it's 4 times greater in series than it is in parallel. Explain why the current is not 4 times greater than I1. Okay, let's see. What do I know about current? I know that V is equal to IR. Okay, so I will be equal to V divided by R. But for both parallel and series, the V is still the same. We still have 12, right, which is the EMF. But we want to find the total resistance, right? Let's find, because when we're looking at I, we're looking at the total resistance, right? So let's first start with total resistance. But in series. So in series, you have X plus X plus little r, right? Plus that little r, because they're sort of all of them in series. So let's say X is 8, right? So we have 2X plus r. So let's say X is 8. We're going to have 16 plus, let's say r is 3. 16 plus 3, that's going to give you 19. So that it sort of makes sense. We're just using examples, guys, so that it sort of makes sense, right? So this is the total resistance when we are in series. But let's go in parallel, right? So let's go in parallel. The total resistance, okay, in parallel, right? We already calculated X over 2 for that. So in parallel, we're going to have X over 2 plus R. We said X is 8. So we have 8 over 2 plus 3. That's going to give you 7. You can see the resistance of these components themselves, X and X plus X, X2X, X over 2, that's what's 4 times as great. But the total resistance, 7, is not 4 times as 19. So the total resistance in these circuits is not 4 times at all because of internal resistance. It's not going to be 4 times. If it wasn't for internal resistance, evidently you'd see 8 over 2, that's 4. 2x, that's 16. 4 times 4 is actually 16. But because of this little guy we call internal resistance, that law has been broken. It's no longer true. So it means that due to internal resistance, the total resistance is not going to be the same. Hence, the current will not be 4 times as great. Does that make sense? So we're writing it in words. We're now just going to say due to internal resistance, okay, so the total resistance for the series is not actually 4 times as great as for parallel. Hence, the current will not be 4 times as great because of internal resistance sort of affecting that thing, right? Kirchhoff's law. I love Kirchhoff. Very great guy, neat guy. So Mr. Gustav Robert Kirchhoff came up with some laws, right? Gustav. You know, Gustav was a pretty guy. I would have enjoyed living in this guy's age, right? So Gustav came up with a second law. The second law for Gustav is the conservation for energy, and it says that the sum of the total potential differences in a circuit will be equal to the sum of the EMF. The total EMF that you have will sort of be equal to the sum of the total, potential differences that you have across that entire circuit. So it means that if you're considering Fig 5.1, if you look at Fig 5.1, our total EMF is 12, our current is 1.2. So if our total EMF is like that, then our current is 1.2. It probably means that your EMF, which is 12, will be equal to, right, IR, because V is equal to I times R. So it means that your I is going to be, like I've said, evidently 1.2. Your total resistance is basically 2x plus 1.2 times your internal resistance R. But this can be rearranged, guys. This can be rearranged into just 1.2 open bracket 2x plus R if you factor out 1.2. If we go on that specific circuit, again, we have 12 being our EMF, our current 3.0, our resistance for that, guys, that's basically x over 2 plus your internal resistance, which will be R. Why? Because this is IR. So the total potential difference will be equal to the current times 2x plus the current times that small little guy R. Use the equations in I2 to calculate the resistance X. 1 mark. Come on, guys. But it's cool. So we have 12 being equal to 1.2 open bracket 2x plus R. Divide both sides, you get 10 is equivalent to 2x plus R. Let's call this equation 1. We have 12 being equivalent to, 12 being equivalent to 3 x over 2 plus R. We divide by 3, we get 4 being equivalent to x over 2 plus R. That's equation 2. Right, so we can sort of find R from this case. We know that from 1. This is math, guys. Physics is just math. 10 minus 2x, complicated math. 10 minus 2x, right? So if you substitute on that, we have 4 being equal to x over 2 plus open bracket 10 minus 2x. So we're going to have x over 2 plus 10 minus 2x will be equal to 4. Put that on the other side, we have 6 being equivalent to 2x minus x, that's just going to be 2x. So 10 minus 4, that is 6, but 2 minus half, that's just 3 over 2. Okay, so 2 minus half, that's just 3 over 2x. So x will be equal to 2 times that is 12 divided by 3. So your value of x would just be 4 ohms. So x will be 4 ohms. And they give you 1 mark, these guys. Right? So for math, they don't really award you much, right? You do a lot of math, but do it in your head, right? That's what they assume. Okay. Calculate the ratio of power transformed in one resistor of x over power transformed in one resistor of x in Fig 5.2. Okay. So, what do I know? I know that power is equal to the work done per unit time. But I know that potential difference V is basically the work done per unit charge. So the work done will be equal to VQ. So I can substitute that, then I get VQ divided by T. But Q over T is essentially I, so VI will be equal to your power. But I know that V is equal to IR, so it means that V is going to be I squared R, right? So if I want to find the power transformed in one of those resistors, I'm going to use this little formula, right? So I'm going to have 1 I squared R divided by I squared R. For both scenarios, this is in 5.1, then this is in 5.2. So if we start in 5.1, our resistance is 3, guys. Our resistance is 3. But our current, if you look here, we're going to use Gustav's second law. Sorry, don't say Gustav. You won't get him out. It's Kirchhoff's. Gustav Kirchhoff's first law. So if you're here, evidently we're going to get this being 3. But our current is going to be the same, 1.2, 1.2. So our current is 1.2, right? And then our R is actually 3. But if you go here, our current is not 3, as we are told here. And then our resistance is just 3. When things arrive here, current is going to branch, right? Let's say current is going to go up or it's going to go down. So we sort of talk of current as if it's now charge carriers, right? But just know current is the rate of flow of those charge carriers. But we sort of talk of current as if it's existent, right? But sort of if we have 3 coming up, according to Kirchhoff, they're going to branch. Some go up, some go down. Then they're going to branch in a specific ratio based on their resistance. In this case, it's the same. So we're going to get 1.5 over here, 1.5 over here. So that when it's done, they come, they reunite, 1.5, 1.5, they both go home with 3 amps. Okay, so when it arrives at a junction, current splits, right? And when current splits, we can sort of find that split based off the values, sort of the ratios that you would have. So in this case, we have 1.2 squared. Here we have 3 times, in that case, we have 1.5, all of that squared. You punch it on your calculator, you get 0.64. 0.64. The resistors in Fig 5.1 and Fig 5.2 are replaced by 12-volt filament lamps. So we're substituting it with a filament lamp, as you can see over there. Explain why the resistance of each lamp when connected in series is not the same as the resistance of each lamp when connected in parallel. So this needs you to be a little bit clever. So we're substituting it with 12-volt 12-volt lamps. Okay, so if this scenario and we're replacing it with a lamp, guys, I need you to be clever. So you're replacing this with a lamp. I can't draw a lamp. So we're replacing this with a lamp, like so. Then this is a 12-volt lamp. This is a 12-volt lamp, and we're replacing this with a 12. We're not going to use all 12 volts, right? We don't need that. But we are sort of going to have something like this. Then here we're going to have something like this. Okay, so a specific current is going to flow through this thing, right? Specific current. But then if you look at the potential difference that's going to be here, the potential difference that's going to be here is just going to be 6 volts. The potential difference that's going to be here is also going to be 6 volts. Then the current is going to be 1.2. The current entering is going to be 1.2. But if you look at it, like I said, electrons branch, charge carriers branch when they reach a junction, but they go with that same amount of energy. So here, you're going to have 12 volts. And then here, you're also going to have 12 volts. The current going through here is 1.5. Then the current going through there is also 1.5. We have this scenario. We have different voltages and different current values for these filament lamps in 2 scenarios. One scenario like that, then the other scenario like that. But we know that, if you remember correctly, graph for voltage against current for filament lamp, we want to be clever, right? The graph for voltage against current, the IV graph. So let's put an IV graph like so. Now let's be right. It's going to look like this, sort of a little f. It's going to look like this, right? So you can sort of see a variation of current and voltage as we are moving, right? So I and V, they vary. They're not the same. So it means that the resistance, which is the ratio of V over I, will not be the same, because you can see on this graph, the gradient is constantly changing. For a filament lamp, it's different from a resistor. A resistor is made up of a metallic wire, so the resistance is basically the same. But when you look at filament lamps, it's not the case. We're not going to have the same resistance. It's just not going to work. What's going to happen is that you're sort of going to have a variation of I and V. So if we're looking at this scenario, explain why the resistance of each lamp when connected in series is not the same as the resistance of each wire. So the resistance will be the gradient of that graph. We can safely say that the resistance of a lamp sort of changes with V and I. So the resistance sort of changes with V and I, and the V or I in parallel is actually greater than in the series circuit, right? Hence, this is me just being a little extra, hence you don't need to do that. Hence the resistance, right, will not be the same. So since V and I vary on the specific graph and they change, so it probably means that the resistance, which is your gradient, is not going to be the same. So it's also going to change. Hence, we can safely say that the resistance when connected is not going to be the same. So one difference between longitudinal and transverse wave. We have longitudinal and transverse waves. What do we have? For longitudinal, we know that the vibration, right? The vibration for longitudinal is that it's parallel to energy transfer. So for longitudinal, is displacement of particles, as you can see, that are parallel to the energy transfer, whereas it is perpendicular for transverse wave. What is the similarity that or you can also say longitudinal waves cannot be polarized. Longitudinal waves can transverse waves, can be polarized. Longitudinal waves cannot be polarized. If you want to know why, check out my video on polarization. It will explain a lot of things. I made a playlist for polarization as well as explaining in depth. I was just solving a lot of questions, so I would highly recommend that you check that out. But the similarity, they're both progressive waves, so they both transfer energy. So that's a plus, right? They both transfer energy from point A to point B, will transfer energy, or they propagate energy. That's important for you to be thinking of that. A laser is placed in front of two slits. A laser, hits like that, splits, reflects, and attaches like that, right? So a laser does that, and then it emits light of wavelength 6.3. The distance from slits to the distance to the screen is 2.5. The separation of the slits is 0.35. An interference pattern of maximum and minimum is observed. Explain why an interference pattern is basically observed. So we want to explain what interference is and how that works. So waves must come with a constant phase difference. They must be having the same phase difference. They must be in phase, right? So it can't be a wave if you have something like this. You can't have another wave like this, right? They have to be having the same wavelength, or the same constant, rather I say the same constant phase difference, right? So they're supposed to be coherent when they're coming from the slits. So if they're going here, then when they arrive here, they're supposed to be coherent, having the same phase difference. So that's the first point that you're just going to write. So you're going to write that waves from slit must be coherent. Coherent meaning they have a constant phase difference. Lock in, right? The second point, okay, the second point is essentially going to be the waves will now overlap. Okay, the waves are going to meet and then they're going to overlap. When they meet like this, they're going to overlap, right? So the waves overlap or a path difference. So as waves are arriving at the screen, they're sort of going to overlap one over the other, and they're going to have a phase difference that's constant as well as a path difference. So as long as there's that phase difference or that path difference, they're going to meet at a specific point. They're going to overlap one over the other, and then you're sort of having now maximums and minimums, maximum interference or minimum interference because certain conditions have been met, right? So a maxima is observed, right, when path difference is just n lambda, where n is an integer, right? So waves must be coherent. They have the same phase difference, right? They're coming in phase. In phase meaning that the difference in their movements, right? Some will be moving up, some will be moving down, will be the same. Sort of their differences in phases is going to be the same, so they're going to be coherent. They're going to overlap at the screen with that phase difference. That's constant, mind you. So we're going to see a maximum, right? A maximum when the path difference is actually n lambda. What is the path difference? If one wave travels 4 lambda as a distance, other travels 3 lambda, your path difference will be lambda. So your path difference is basically the differences in the paths that they're going to take. These paths are not equal, right? One path is longer than the other. For example, if we're supposed to go to this point, right? Look at that. That path is longer, but we want to find out by how much. If that path difference is n lambda, where n is an integer, we're going to have a maximum. If it's not n plus half lambda, we're going to have a minimum, right? If the phase difference is an integer times 360, we're going to have a maximum. If the phase difference is not, we're going to have a minimum. So we're sort of just, playing around with where we can get a maximum, where we can get a minimum. Because if the phase difference is actually 360, they're going to arrive in phase. If they arrive in phase, they're going to add up and be bigger. So you're going to get a maximum, right? I hope that makes sense. Moving on to the next question. Calculate the distance between adjacent maxima. What do we know? We know that lambda is essentially ax divided by d. So your x will be equal to d times lambda divided by a. Right? Your d is actually 2.5. Your lambda 6.3 times 10 to the power of -7. Your a 35. 0.35 actually millimeters, right? So 0.35 times 10 to the power of -3. So that's going to give you an x of 4.5 times 10 to the power of -3. So you're going to have 4.5 times 10 to the power of -3. Then it explains the effect, if any, on the distance between the adjacent maximum when the laser is replaced by another laser emitting ultraviolet. As you can see on the graph, I know that Robert is very ugly except Grace. Okay, so I know this order, and I know that ultraviolet is coming here, and then visible light is coming here. So I can see that since I've been told that it's visible light, how am I knowing this? Look at this. The laser emits light, right? So it means that visible light had a specific lambda, but if I'm looking at ultraviolet, it's going to have a smaller lambda, right? And if you look at this, if lambda is small, if you look at a and d being constant, if lambda is small, x is also just going to be small, because if lambda is small, it's going to diffract less, hence it's going to have a smaller separation. So we can just write that out, have a smaller separation because of that smaller wavelength. Okay, number 7, yay, atomic physics. In the decay of a nucleus of 210-84 Po, an alpha particle is emitted with an energy 5.3 milli-electron volts. The emission represented by this nuclear equation. So we have an alpha emission occurring, releases an alpha particle, a nucleus, and some little energy. On figure 7.1, complete the number and name of the particle or particles represented by A and B. So if you look at A, during alpha decay, an alpha particle is essentially 4, has essentially 4 and 2 over there. So it means that if you're comparing X, your A is just going to be 210 minus 4, which is just 2 or 6. Your B just going to be 84 minus 2, which is 82. Because if you look at it, the nuclear particles are supposed to be conserved. We don't lose or make particles. We just rearrange formations, right? We don't make completely new particles, and we don't destroy particles completely. They just change their nature. So it probably means that for A, the number is just going to be 2 or 6. And that number represents the nucleon number, which is the combination of neutrons and protons. Then for B, we're going to have 82. What does 82 represent? 82 just represents protons because 82 is the proton number. 7, form of energy given to alpha particles in the decay of 210. So guys, I want you to think, what energy could this possibly be? It can't be gravitational. It can't be chemical. Well, that wouldn't make sense. What only makes sense is kinetic energy to enable that alpha particle to move. It is as it's being ejected or sort of expelled from the nucleus. So as the decay is occurring, the alpha particle is sort of going to gain a little bit of some kinetic energy. All right, a little bit of some kinetic energy, or EK if you're short. A sample of polonium, right? Polonium. So we have a little bit of a polonium element. Polonium 210-84 Po emits 7.1 times 10 to the power of 18 alpha particles in one day. Calculate the mean power output from the energy of the alpha particles. What do we know? What do we know? I know that power, right? Power is equal to the work done per unit time. But my time, guys, come on. But my time, I have 24 hours, 3,600 seconds in an hour. So my time is 24 times 3,600. But my energy is essentially my energy transferred. My energy transferred, the energy that I'm getting out. Right? That's going to be equal to, how many particles do I have? I have 7.1 times 10 to the power of 18. But one particle, guys, millielectron volts, probably done in electric fields, not highly examinable, but I'm just going to teach you, pretty fun. 5.3 milli-electron volts. So, milli-electron volts, what this essentially tells you that when you're comparing an alpha particle, it's one particle. So the work done per unit charge, we only have one particle that we're dealing with in this case. So it means that if you have 5.3, mega is times 10. So it's mega, it's mega electron volts. So it's with energy of 5.3 mega electron volts. So mega is 5 times 10 to the power of 6 times an electron volt is 1.6 times 10 to the power of negative 19. So this is the amount of energy that you'll be getting out. 5.3 times 1.6 times 10 to the power of negative 19 times 10 to the power of 6. So it probably means that because this is the energy that you're getting out, 5.3 per unit charge, per output that you're getting, per each alpha particle. So if you have 7.1 times 10 to the power of 18 times 5.3 times 10 to the power of 6 times 1.6 times 10 to the power of negative 19. and you divide all of that by your time, 24 by 3600. That's going to give you about 70 watts, right? So what are we doing? We want to find our time. 1 day, 24 times 3600. We want to find our energy transferred. How many of our particles do we have? 7.1 times 10 to the power of 18. How much energy is one of our particle giving us? 5.3 mega electron volts. So to transfer mega electron volts to go to joules, we simply multiply by 1.6 times 10 to the power of negative 19 times 10 to the power of 6, because E is sort of representing 1.6 times 10 to the power of negative 19. So essentially, that is how we think about it. Then we plug in our values, then we get an output power. Moving on to the next, off we are done, right? So it was a pretty fun paper. So there are a lot of concepts that you just needed to sort of have your head wrapped around, but they're not really that difficult. I really hope that it was helpful and you're able to think about it and solve it. Thank you guys for watching, and I'll see you in the next one.